For researchers from all disciplines, Iceland is a unique experimental laboratory. Geochemist Roy Price conducts research at Stony Brook University in New York. An international research project in which NASA is also involved takes him to the north of the island. Large parts of the northwestern coast of Iceland are characterized by deep fjords. These elongated inlets were formed thousands of years ago when glaciers shifted towards the sea. The fjord is the target of Roy Price and Icelandic diver Elundur Bogason. In 1997, Bogason made a spectacular discovery here, a geothermal vent over 50 meters high called the Great Streeton.
Right. And then what's coming to the bottom?
Conditions that could be found on Earth 4 billion years ago prevail around this hot water source, the point in time when life emerged on Earth. Roy Price even compares the conditions in the Icelandic fjord with another planet in our solar system.
Mars used to be an ocean world about 4 billion years ago before it dried up. So it had an ocean, half of the planet was ocean, and it was, as it was drying up, it formed these large lakes. And in one of these areas, there was some hydrothermal activity, very similar to what we see here in the fjord. And so that is the connection between why I'm here, the connection with Mars, and habitability. We want to know if that ancient system was actually livable. These are the syringes we use to talk through.
The key to the origin of life is said to lie in the biochemical processes in the environment of the Streeton. To get to the bottom of these, Roy Price needs a sample.
So the samples I collect for the fluids, we're doing basically calculations for bioenergetic potential. How much energy is available on the mixing of the two fluids, the vent fluid and the seawater. By doing these calculations, we know precisely how much energy is available for microbes to utilize. And so knowing that, we know also how habitable the environment is.
So if you go there and test it,
we can check the temperature and then collect a sample.
And see if it's worth taking samples.
Okay, let's get ready to dive.
Okay.
Okay, all right.
The weather is in the divers' favor today.
So the diving site that we're going to is called Big Streeton. That's located this direction. It's about almost a kilometer that direction. And we'll just cruise out. There's a buoy there, and we'll just connect the boat to the buoy, and then we'll go in the water.
The Streeton is unique in the world because it is so close to the water surface and easy to reach for divers. Most hot water vents form at the seams of Earth's plates, deep on the ocean floor. Scientists estimate the age of the Streeton at about 20,000 years. Before that, the area was covered by a kilometre-thick glacier. It was only when the glaciers retreated at the end of the Ice Age that they left behind these elongated sea bays, otherwise known as fjords.
So we think that that may be when the cones started forming, maybe 20,000 years ago. And so over time, it just builds up more and more and more. And so now it's 55 meters tall and maybe 30 meters around at the base. It's really a giant monolithic structure, the biggest one. And there are many others associated with it, close to it.
Okay.
After a few meters, visibility improves. The Streeton appears in front of the two researchers. At one point, hot rising water collects in a small overhanging rock, and the geochemist measures and notes the temperature. Using a special syringe, Roy Price takes a sample of the hot water source that is as pure as possible. Impurities could affect the results of the chemical analysis. The water, which has a temperature of over 70 degrees Celsius, begins its journey as groundwater. In the interior, it is heated by geothermal processes, follows underground cracks and fissures, and emerges here. Minerals form the material for the construction of the vent, which continues to grow upwards. Although the ambient temperature is only just above freezing, the divers can warm up briefly thanks to the hot stream from the Streeton. After 20 minutes, the dive is over.
It was great, amazing. 70 degrees Celsius. Lots of hot water coming out everywhere. Really amazing.
Roy Price's research focuses on the biochemical reactions that take place in underwater sources. The energy released there could be a key factor in the emergence of life.
All life needs energy. So when two compounds react with each other, there's electron transfer. Microbes know that. They tap into that reaction, and they steal some of those electrons for life, to live, to move around, to build biomass, and to reproduce. And that's a real connection between geology and life, and Earth, and the origin of life, or how life evolved. It's all connected. So as long as there's an energy source, and that's derived from the mixing of the two fluids and a generation of disequilibria amongst the mixing environment, as long as there's energy to be had, the system is habitable.
Similar processes could have taken place on Earth and Mars 4 billion years ago already. Whether they are actually a prerequisite for the emergence of life, research has yet to prove.